Okay, so in the last class we introduced the decomposition of the stress or strain into two parts. So the strain could be shown as uh, where epsilon b is simply the trace of the strain tensor, okay, or the volumetric strain plus the deviatoric part of the strain. Now you see, if you look at this part of the strain, that actually looks like this. So the diagonal components are epsilon v by 3 and rest are 0. Okay. So basically, if this is the only component of strain, then a differential element, okay, I mean, if this is the differential element, okay, so that simply transforms into a scaled down or a scaled up version of itself. Okay, so each dimension is elongating or or compressing by the same amount or the same fraction. That's what this means, right? So mm, essentially essentially you have scaling up or scaling down going on through this volumetric part of it. Now what else could be there? There could be this scaling in the form of strain, and there could be non-uniform stretching. That means uh, longitudinal strain or normal strain on each face which is non-uniform, and the third category is shear. Now these two are clubbed into this tensor right there, the deviatoric part of the strain. Okay, and as we have seen that at least in elasticity, the deviatoric part of the stress and the strain are proportional to one another. Okay. Uh, what else? Yes, we were talking about stress and we are talking about the invariance of the stress. Now let's look at the invariance of the stress. Uh, so this quantity, again, you can define three invariants. Can you tell me what is going to be the I1 of S? Or we would simply call it J1. If we denote the invariance of stress tensor as I's, okay, so then with for deviatoric stress tensor, we will simply denote them with J's. So what is the value of J1, the first invariant of the deviatoric stress tensor?
Epsilon V.
Sorry?
Epsilon V.
Epsilon V. I'm talking about the stress tensor.
So sigma 1 plus sigma 2 plus sigma 3 divided by 3.
See, be it the deviatoric stress or the strain tensor, the first invariant, which is essentially the, the stress, okay. So that quantity would be how much?
Sigma 1 plus sigma 2 plus sigma 3 divided by 3.
Oh goodness. First of all, where do you get the 1 by 3? Okay. When I'm talking about trace, that is simply the sum of the diagonal components. Okay. And don't think in terms of principal coordinate system. Think in terms of the, the global Cartesian coordinate system. Okay. And first of all, we are not talking about the total stress tensor. We are talking about a Deviatoric stress tensor. So this looks like this, right? The shear components, as we know, are same as the stress tensor, right? Sorry, this one, the first is the direction, yes. Okay, so what is the trace of the Deviatoric stress tensor?
Sxx plus Syy plus Sz.
Okay, so the sum of the diagonal terms, right? And each of the diagonal terms, for example, Sxx is let's say sigma xx minus sigma m, where sigma m is sigma xx plus sigma yy plus sigma zz divided by 3, right? So this quantity essentially becomes sigma xx plus sigma yy plus sigma zz minus 3 times sigma m. Now sigma m being this quantity right here, this is supposed to be 0. That's how the Deviatoric stress and the Deviatoric strain tensors are defined. The trace has to be 0. Okay, is it clear?
Yes, sir.
Okay, okay. So now let us talk about the J2. Okay, you recall how you define the second invariant. So you take the the principal determinants. Okay, so basically these two, and then the third one will have this row and this row. Okay, so write down the expression for J2. So as you might recall, the stress tensor can be represented as sigma m times I plus S, where sigma m could also be written as the negative of the pressure. So did you get the expression for J2?
Sir, Syy into Szz minus sigma Zy
Okay. So whatever expression that you have got, substitute for Sxx, Syy, and Sz. For example, Sxx would be twice sigma xx minus sigma yy minus sigma zz by 3. One question. Do you know when does your session dissolve? This summer one? Or in other words, how much time do we have?
আগস্টের ফার্স্ট উইকে এক্সাম।
Okay, so we have this month and the next month, right?
Yes.
Okay. Did you get any expression?
স্যার হচ্ছে কিন্তু অনেক বড় এক্সপ্রেশন আসছে।
Okay. Yeah, I believe that big equation can be reduced to something like this. And I'm not quite sure about the shear components. Does they come with a coefficient of 2? Should they come with a coefficient of 2? Or coefficient of 3? I'm not quite sure. So I believe you will get something like or no, no, it's not 3 right there. So yeah, this sum is 1 by 6 plus sigma xy squared, sigma yz squared plus sigma zx squared. Yeah, I think this is the correct representation. Are you able to simplify into something like this? One more thing, in the last few classes you had mentioned that you have been made familiar with the invariants and the principal directions. I believe that those are the things with reference to the regular stress tensor. Okay, but have you been made this much familiar with the deviatoric stress tensor? In theory of elasticity, did sir discuss this much about the deviatoric stress tensor as well?
No, sir.
No, sir.
Okay. It's because possibly in plasticity, the deviatoric stress tensor is basically the only thing that we are interested in. Okay, in as far as plasticity goes, so we need to be able to make ourselves extremely familiar with all the properties of the deviatoric stress tensor. Okay, and that's what this class is about. So when you would be looking back at this class, today's class, in 3-4 weeks from now, so this class is going to be the most important class so far. But can you get this expression? Did you get this expression? I may be wrong with the coefficients, okay, but something like this will come. Or maybe this whole thing just comes with a negative sign. Have you got this expression? Okay, so if it is turning out to be difficult, let me tell you that just like I2 for stress, okay, sorry, I2 for stress, or there are other ways to represent I1, I2, I3. For example, you can do this I2 and I3. Okay, so just like I2 for stress, we know that this eventually turns out to be, or for any arbitrary tensor, okay, the second invariant is essentially trace of S whole squared. I hope you recall this representation, minus trace of S squared. Okay, so that would probably help you in simplifying the expression. Okay, so we showed that this is true for any arbitrary tensor. Okay, this expression right there. Okay, so we can take help of this identity right here. Okay, and as we just showed that the first invariant is 0, so this quantity is essentially minus half of trace of S squared. And trace of s squared, we discussed that trace of s squared is summation of I s squared I, or summation over I, summation over k is ik is kj, is kik is ik is ki, but then s is a symmetric tensor, so this can be written as is ik is ik, okay, because s is a symmetric tensor. What basically means is you take individual terms of the deviatoric stress tensor, multiply with itself, okay, and add them up. So it is essentially minus half summation over I, summation over j is ij is ij. Okay, so try doing that. We have already proved that this expression right here, the j2, this determinant, sum of the determinants, is essentially turns out to be this. Look at one of the previous classes where we derived that, okay, and that is true for any arbitrary tensor, okay, not even symmetry. So if that is true for any arbitrary tensor, that is obviously true for deviatoric stress tensor. So we can take help of this expression right here, and in that we can substitute that the trace itself is 0. Okay, a few other things I would like to show, because that would help us. First of all, if I write q equals this, okay, where n1, n2, and n3 are principal directions of the stress tensor, then we know that q transpose, okay, sorry, q sigma q transpose possibly, yeah, q sigma q transpose is diagonal. Now, as you might know, the stress tensor has okay, we just wrote this down. Okay, the two parts, one where it is hydrostatic. So when it comes to stress tensor, we say it hydrostatic. When it comes to strain tensor, we say volumetric. So one part is hydrostatic, the other part is deviatoric. Now, if I do this this thing right there, this actually becomes sigma m times q I q transpose. Okay, now q I q transpose essentially is this part is q transpose, but then q transpose is the identity tensor. Okay, plus q is q transpose. Okay, now look at this matrix right here. This actually looks like this. Now, what is sigma m? Sigma m is 1/3 of the trace of the 1/3 of I1 of sigma, or the trace of sigma, or the stress tensor, which basically means sigma m itself is an invariant. Okay, but what do I understand out of it is that, you see, of the two matrices, if one of them is diagonal and the sum is also diagonal, then there is only one way that can happen. That means the second tensor is also diagonal. That means the principal that means the same set of orthogonal tensor that diagonalizes the stress tensor also diagonalizes the deviatoric stress tensor. Or in other words, the principal directions of the stress tensor are also the principal directions of the deviatoric stress tensor. Okay, so that means with reference to us being able to represent stress like a vector, okay, we can do that with as a sum of the hydrostatic and the deviatoric part. You know, the hydrostatic part having an identity tensor in itself, that any set of orthogonal basis is actually will diagonalize the identity matrix. Okay, any set of, so that means the principal directions of the stress tensor will also do the same. Okay, now imagine this is a line which makes equal angle with each direction. Okay, I don't know how much angle that should be. Actually, I know that angle is each of this angle is cos inverse 1 by root 3. Okay, which basically means for this line, okay, L equals M equals N 1/3 square root of 1/3. Okay, so that is the hydrostatic direction. And imagine there is a plane perpendicular to that direction. So this plane is perpendicular to that direction. Okay, so if I want to represent stress as a in the principal coordinates, so the stress tensor is a vector in principal coordinates, strictly in principal coordinates. So let me put a hat over here, or maybe something else, maybe a star right there. Okay, so sigma 1, sigma 2, sigma 3, and that actually is a sum of sigma m, sigma m, sigma m, okay, plus S1, S2, S3. Okay, so that means I can represent the first vector, which is sigma m thrice. Okay, that is a hydrostatic vector, hydrostatic stress vector. Okay, in the principal coordinates, and then to give the deviatoric part, which is actually perpendicular to the hydrostatic direction. That's what we have been talking about, right? That the product of these two must go to 0. Okay, so basically, if I take a product, the product itself, the dot product, all I mean is, so so this dot date, this would be sigma m times S1 plus S2 plus S3. Again, S1 plus S2 plus S3 is the trace of the deviatoric stress tensor in the principal coordinates, but the trace, or J1 being an invariant, that is the trace all the time, which basically means the trace itself is 0. Okay, so that this dot product is 0, that means these two vectors are orthogonal to one another. Okay, and this right there becomes our S star. Okay, represented as a vector in principal coordinates. Okay, so you can imagine a plane that has equal intercept with all the three axes. Okay, again, go back to one of our previous classes. We talked about octahedral planes. Okay, octahedral planes. So the octahedral plane on the first quadrant. Okay, the octahedral plane on the first quadrant is essentially the deviatoric plane. Okay, we talked about octahedral plane in relation to the flow in relation to slip, where you discuss the slip planes on a FCC crystal structure. And there we talked about there are 4 octahedral planes, and on each octahedral plane there would be 3 closely packed directions. Okay, the octahedral plane are most densely packed planes. So on those densely packed planes, the close packed directions Okay, essentially where the atoms are literally, when modeled as hard sphere touching each other. So so together they make for 3 times 4 12 slip systems. So we discussed that in probably the second class. Okay, go back to that class right there. So it's not the same octahedral plane. Okay, because this time we are not talking about microstructure. This time we are talking about a macroscopic representation. Okay, but again, the amazing thing is that with in relation to plastic flow, in relation to plastic deformation, we are again stuck with one octahedral plane. Okay, it seems that the octahedral plane has a place, preference towards plasticity. So we end up having another octahedral plane. So this octahedral plane is actually your deviatoric plane. That is the plane in which there is no change. There is no change on the hydrostatic component of the stress. The only component of the stress that changes is the deviatoric stress. Okay, and if you're moving along this, this line right here, which makes equal angles with each of the principal directions. Okay, in that direction there is no change of the deviatoric stress. There only the hydrostatic stress changes. Okay, so this in this axis right here makes equal angles with the principal directions, and this plane right here makes equal intercept with each of the principal directions. Okay, so we learned two things. One is the stresses, that is hydrostatic and the deviatoric part, can be represented as two orthogonal components. I have been literally mentioning that they are orthogonal. They are orthogonal. Okay, and there now we can see in the literal meaning of it how they are orthogonal. And I mean, they're so orthogonal that their dot product is 0. And what we learn is that the principal directions of the stress and the deviatoric stress tensor are identical. Okay, which is a blessing for us, that now that we can look at the stress tensor or the deviatoric stress tensor in the what do you say, in the same principal coordinate as a stress tensor, and we are able to represent that as a vector. Achha. Now you see, if the second invariant is an invariant, okay, and the first invariant is an invariant, and since this is the general representation for the second invariant involving the first invariant and the trace of the square of the matrix, okay, so basically we know that the trace of the square of the matrix, okay, is also an invariant. Okay, and as you can see, we have already shown this, right? First of all, let me show you this. Take any arbitrary symmetric tensor, okay, and QSQ transpose, let's say, diagonalizes S. This time S is not a deviatoric stress tensor, it's any arbitrary stress tensor. Multiply that with QSQ transpose. That essentially becomes this part right here, gives you identity tensor. So this essentially becomes Q transpose. Okay. So so you know that in the principal directions, this one is diagonalized, and so is this one. Okay, and when you take this, do that multiplication, you would end up having S1 squared, S2 squared, S3 squared. Okay, now this shows that the principal directions of S, which as we know is principal directions of sigma, not only diagonalizes S but also diagonalizes S squared, and using the same principle can be shown it diagonalizes any higher powers of S as well. Okay, so this this stress right here, okay, so this, which basically means this can also be written as minus half of S1 squared, S2 squared, and S3 squared, because trace of S squared is also an invariant. Okay, and if you substitute S1 equals sigma 1 minus sigma m, for example, sigma m is trace of S divided by 3, which is sigma 1, plus sigma 2 plus sigma 3 divided by 3. Okay, so if you substitute for that in this expression, you would get this expression right here, minus 1 by 6, then no shear term, but only the normal terms, which is sigma 1 minus sigma 2 whole squared, plus sigma 2 minus sigma 3 whole squared, plus sigma 3 minus sigma 1 whole squared. Now I'm just giving you all of this right away. Okay, but I need you to derive all of this. Okay, so you have around 10-15 minutes of the class. So what you can try right now is to derive all of these expressions. I mean, this right here. Okay, so first using this relation, try to get this. Okay, and then using this, try to, I mean, this obviously would give you this expression right here. Okay, if this gives you this, then this right here would give you this. So try to get this expression right here. Could you understand most of the things that I said?
Yes, sir.
Okay. So does all of this make sense, or you are confused with some part, or you don't agree to some part? Is that something that you don't agree, or it looks all consistent? Okay, I believe now you can try to derive it. Okay, try to get that expression right there, involving sigma x and sigma y. And so you might notice here each tensor is represented in 3 forms. One is the global Cartesian form, where I'm writing it as sigma xx, sigma yy, sigma zz, sigma xy, yz, zx, etc. What else I'm doing? I'm also, you see, representing them in the principal coordinates. Okay, and then in the principal coordinates, because they can only be the directions of the force and directions. So in principal direction, since there are only normal stresses, so the direction of the force and direction of the plane, okay, the normal to the plane, are coincidental. So in the principal directions, what I'm doing here is representing them as vectors. Okay, and that ability actually lets us see the stress tensor. You see, we cannot look at a stress tensor, because a stress tensor would be at best a six-dimensional vector. Okay, even when I'm representing that with void notation. Okay, stress tensor in its global Cartesian coordinate system is essentially a 6-dimensional vector, and for that I need to have a 5-dimensional screen and a 5-dimensional eye, which I don't have. So instead, what we are doing is we are taking everything into the principal coordinate system. Okay, and which is basically looking at the stress from a different coordinate system. So axes are at different angle. Okay, with the global Cartesian. So, but there is one principal direction, or more than one principal direction, from which if I look at the stress tensor, it looks diagonal. So essentially I can represent that as a vector, and being able to represent that as a vector allows me to visualize the stress. Okay. Now, if certain stress value, let's say the magnitude of the deviatoric stress tensor, okay, were to remain within certain value for the structure to remain intact or structure to not have any plastic deformation, if the magnitude of the deviatoric stress tensor should be within certain limit, so I can represent that by a circle on the deviatoric plane. Okay, and that lets me have an idea of an yield surface. Okay, so that's what you do next in our next class, talk about yield surfaces. Okay, and because we will be doing such, your assignment for the next class, next Monday, before coming to next Monday, read about theories of elastic failure. Okay, there are plenty of them. Maximum principal stress theory, your maximum shear stress theory, or Tresca theory. There is distortion energy theory. There is you see your what else? Maximum strain theory. There are a lot of theories. Okay, I need you to go through all of them. Okay, and you can take any design book from undergrads. Okay, in my mind, the first book that comes in my mind is Bhandari. So you can get that book, and you will probably find a chapter where it discusses about principle. I mean, sorry, mm, the failure theories. Okay, so look at those failure theories. Okay, and every time the author discusses about a failure theory, he also mentions where it is applicable. Is it applicable to brittle materials? Is it applicable to ductile materials? So read about all of that thoroughly. That is your only assignment for the day. Okay, and you have 5 days to go. So pay a big attention. We are heading towards yield surfaces. So that's why it is important. Okay, so I'll stop here. Okay, unless you have any other questions, and I'm sure you can derive on your own. Okay, if you are stuck at derivation, let me know, maybe through mail or WhatsApp. I'll definitely try to help you, okay, with the derivation. But for the time being, this is an assignment, and also the other thing that to read about the failure theories is also an assignment for you. Okay.
Okay, sir.
Okay, so unless you have any other queries,